All right, so 8.4. So this is testing claims about the standard deviation of variance. So in order to do these, it's like I said, they're all done exactly the same thing. You just have a different distribution. For proportion, it was z distribution. Mean, it tended to be a t distribution, and for standard deviation and variance, it's a chi-square distribution. So left-tailed, if it's a two-tailed situation, what you're going to have is you're going to have critical values of chi-squared left and chi-squared right. So that's what they're going to look like. If it was just a left-tailed, you're only going to have chi-squared left, and if it's just a right-tailed, you're going to have chi-squared right. Now, if it's two-tailed, the sum of the areas is going to be equal to alpha, but if it's one-tailed, that'll be alpha, or if it's one-tailed on the right, that's going to be alpha. So that's how that works. So remember, these are your critical values. The way you find your test statistic, it doesn't matter what one; they're all actually tested identical. So there's no really there's no thing that you have to do like previously, like in section 7.3. The standard deviation, you had to square root everything, but the variance you didn't. But in this case, neither one, because you're not really worried about their actual value, you're worried about where they live as opposed to our critical value, and they actually share the exact same critical value. So our test statistic would say chi-squared is solved by n minus 1 s squared all over sigma squared. So that's how we find it. So these are just going to be, they're either going to be given or you got to find them. Now what I mean by that is this guy right here is going to come from your claim, and S and N is going to come from your sample. So let's pick one. So let's do birth weights. So a simple random sample of birth weights of 30 girls have a standard deviation of 8.29.5. Usually 0.01 significance level to test a claim that the weights of girls have the same standard deviation as the weights of boys, which is equal to 660. So they want to know if these two standard deviations are the same. They're asking you to test equality. So remember that the restriction on this is extremely strict. That before, either it came from a population that was normal, or n had to be bigger than 30. That's how we would have to do the previous section to test about the mean. Now, for standard deviation, the population must come from a normal distribution. There is no n greater than 30 that'll fix this. So what we know is we're talking about weights, and weights have a normal distribution, so this will work. All right, so number 8. What I know is, I'm going to focus out. Okay, so what I know is that first I have number 1, which is our claim. Well, the claim is about equality. They said that the girls' standard deviation, is equal to the boys, and the boys' standard deviation is 660. So they're saying that the girls is equal to 60.2 HG. So 2, that means the opposite is going to be, well, S is not equal to that 660.2. So we're talking about, again, not equal, talking about a two-tailed situation. So 3, our null comes from equality, so this is going to be the equality. And then our alternative comes from the one that doesn't have the equality. And that's why this is two-tailed, because your alternative talks about your tail. So this is two-tailed. So that means I'm going to be using both these chi-squareds, chi-squared left and chi-squared right. And the sum of the areas is going to be equal to alpha. In this case, alpha is equal to 0.01. So alpha is equal to 0.01. So since I'm going to be using alpha over 2, I'll draw it out here. So number 6, we're going to have a two-tailed situation. Now, remember, it's a chi-squared distribution, so it's a skewed right distribution. But it still kind of looks the same. Like it's a two-tailed, so I'm going to have a tail over here, I'm going to have a tail over here. And, this cutoff is going to be chi-squared left, and this cutoff is going to be chi-squared right. Now, again, if it was only a one-tail on the right, if I was testing greater, it would be this. If I was testing less, it's going to be this. But since it's two-tailed, the sum of these things is going to equal alpha, so this is going to be equal to 0.01. But if it was only one-tailed, it'd just be, 0.05, because it's half of that, alpha over 2. And if it was one-tailed, if it was just a right-tailed, this would just be equal to 0.01 because it'd be one-tailed. And same thing here, if it was one-tailed on the left, this would be equal to 0.01. You wouldn't have the need to cut that in half. But it's two-tailed, so that's what it is. So I might as well find them since I've done all the work of the pictures. So what's this equal to? What's this equal to? So what we're going to do is we're going to go to our chi-squared table, which is right here. And when we read the chi-squared table, remember this says area to the right of the critical value. That's how this is found. So area to the right. Well, if this is, okay, let's just find this one. This one's easy. Area to the right. Well, area to the right of that number is 0.05. And then the degree of freedom, which is one less than how many there were, one less than n. So there's 30 girls, so there's a degree of freedom of 29. So I'm going to go to 29, and 0.005 is going to be 52.336. So this is 52.336. Now, it's kind of nice is remember that if it's two-tailed, these numbers have that, like this number, like the sum of the area is going to be equal to 1, right? So if this is 0.05, this has to be 1 minus that number. So that's at 995. So take that down to 29. That's going to give us our chi-squared value. 13.121. 13.121. So those are your critical values. So to do our test statistic, we need to know if that lives inside here, okay? So what I'm going to do is I'm going to find my chi-squared. Remember, chi-squared, you don't have to square anything. It's label, okay? So chi-squared is going to be equal to n minus 1. So they had 30 minus 1 times the standard deviation, which was given. And the standard deviation, which is of the sample, is S is 829.5. 829.5 squared divided by sigma squared, which is the claim squared. So 660.2 squared. Again, like I said, it's so very similar to what we did before. These just come from chi-squareds. This just comes from chi-squared. But all your whole setup is the same. So plugging this in, 29 times 829.5 squared divided by 660.2 squared is going to give me, this is equal to 45.78. I should go a little more because it says 3780. Okay, good enough. So let's see where that chi-squared lives. You know, where does this chi-squared live inside here? Does it live in the null or does it live in one of these tails? If you notice, this 45 is actually between these two numbers. That 45 is probably about right here. So that chi-squared, which is equal to 45.780, is actually in the null. So in this case, we're going to fail to reject the null. And then we're going to go back to our, actually let's talk about before I answer, because they do the fancy words for number 8. But let's see if the claim is correct or not. So remember that we fail to reject the null, which means that the null is correct, which means the alternative is not, because we're not in the tail, we're actually in the middle. And we map that back, and this actually came from right here. So that means the claim is correct, and the opposite is not correct. So how we write that is kind of dependent on the situation. So the words that they use for that is the claim has equality, and also you fail to reject the null. So there is not sufficient evidence to warrant rejection of the claim. That's how those are done.